All right, let's dive right into this explainer. We're looking at a huge cosmic mystery today, one that's sitting right in our, well, I guess backyard is definitely stretching it. We're talking about Caldwell 42. Some of you might know it as NGC 70006. It's this absolutely massive globular cluster that's been baffling astronomers for literally decades, and today, we're going to unpack exactly why.
To really grasp how isolated this cluster is, we gotta look at this number. 135,000. That is how many light-years away Caldwell 42 sits from Earth. It's plunging through the vast, super lonely outer galactic halo way, way beyond the familiar spiral arms of our Milky Way. It is incredibly remote, and out there in the dark, it's hiding some pretty deep secrets.
And here is where we can actually find it in the night sky, right within the Delphinus constellation. To most telescopes, this distant anomaly just looks like a faint little smudge. But by meticulously mapping the stars in this region, astronomers can make that staggering distance feel real. It's basically a dense sphere of ancient stars, but as we're about to see, it really doesn't play by the rules.
Section 1. The second parameter, a cosmic puzzle. Let's get right to the central mystery here and figure out why this specific, ancient cluster just completely ignores the established rules of astrophysics. So, the big question we have to ask right off the bat is, why does Caldwell 42 break the rules? You see, in astronomy, a cluster's metal content, or its metallicity, usually dictates the color and temperature of its stars during specific evolutionary phases. It's a fundamental rule of thumb. But Caldwell 42? Yeah, it totally does its own thing. It's a bit of an astronomical rebel.
To wrap our heads around this anomaly, we need to understand something called the second parameter effect. This is basically a phenomenon where some unknown secondary physical property alters a star cluster's expected stellar makeup, completely defying what its primary metallicity tells us should happen. We know the primary parameter is metallicity, but what on earth is this elusive second parameter driving all the weirdness in Caldwell 42?
Well, let's look at the actual evidence. On the left, you're seeing what we would normally expect to happen. Caldwell 42 is metal poor, so according to standard stellar evolution, it should have a blue horizontal branch, meaning it should be filled with hot blue stars. But look at the right. The bizarre, honestly contradictory reality of Caldwell 42 is that its horizontal branch is almost entirely red. It's packed with cooler red stars, and that's a feature usually reserved for much more metal-rich clusters. It just doesn't make sense.
Now, for a long time, astronomers really thought they had the culprit nailed down. The prime suspects for the second parameter were anomalous levels of elements, specifically carbon, nitrogen, and oxygen. But when we actually test the molecular bands of these elements in Caldwell 42's giants, they show zero anomalies. None. They are completely normal compared to other clusters with similar metallicity. So the chemical makeup isn't the answer. The plot definitely thickens here.
Section 2. Clues in the stars. Variable star data. Since the basic chemistry was a dead end, astronomers had to look closer at the methodical data collection of variable stars.
Welcome to our Cosmic Detective Board. What you're looking at here are the light curves of pulsating variable stars. These are known as RR Lyrae stars. They physically expand and contract, literally pulsing with light. And by tracking exactly how their brightness dips and spikes over time, astronomers can use them as brilliant blinking beacons across the deep dark of the galactic halo.
So what do these beacons actually tell us? By decoding these RR Lyrae stars using Fourier decomposition, which is essentially mathematically breaking down these super complex light curves, astronomers extract an absolute goldmine of physical parameters. We get the cluster's mean metallicity, a highly precise distance measurement, the mass of the precursor stars, and we can confidently identify it as an Oosterhoff-type I cluster. These metrics are quite literally the cosmic fingerprints of the cluster.
But, as you know, space is incredibly crowded. To get a clean look at the evidence, we've got to filter out the noise. By plotting the kinematics and photometry of these stars, basically mapping how they move and how bright they are, astronomers can cleanly separate the true, ancient member stars of Caldwell 42 in red from the random background field stars in black. It's kind of like dusting for prints and isolating only the ones that actually belong to our suspect.
Section 3. An eccentric orbit, plunging through the halo. Now that we've mapped its internal makeup and separated the members from the noise, let's zoom out to its external movement, because this is where things get really extreme.
Okay, brace yourselves for this one.
According to the research, the total space velocity of NGC 7006 in a galactocentric rest frame is 279 kilometers per second. I mean, just think about that sheer momentum for a second. This massive sphere of hundreds of thousands of stars is just screaming through the outer halo at absolutely unbelievable speeds.
Let's walk through these extreme orbital parameters. It swings out to an apsicentric radius, its farthest point, of 102 kiloparsecs, before diving incredibly deep into the inner galaxy to a pericentric radius of just 17 kiloparsecs. This gives it a massive orbital eccentricity of 0.71. It doesn't calmly circle the Milky Way. No, it violently slingshots through it.
To translate some of this dense astronomical jargon into a more dramatic visual, its current z-coordinate is negative 13.7 kiloparsecs. What that means is, right at this very moment, Caldwell 42 is physically plunging more than 13,000 parsecs, that's over 40,000 light-years, below the Milky Way's galactic plane. It is diving headfirst toward the galactic center.
Section 4. Devoured Galaxy Relic, a Surviving Core. All of these bizarre clues, the red stars, the normal chemistry despite the weird stars, and this extreme plunging orbit, they all point to one incredible conclusion. Caldwell 42 is a relic of a devoured galaxy.
When we compare the orbits, the reality is pretty clear. On the left side here, we see standard Milky Way satellites and native clusters, which generally have low to moderate eccentric orbits. But on the right, Caldwell 42 is completely different. Its highly eccentric plunging orbit definitively proves it did not form the way normal Milky Way clusters do. It wasn't born here. It is literally a cosmic immigrant.
So, here is the timeline of this galactic cannibalism. Step 1. A smaller dwarf galaxy, something kind of similar to the Fornax dwarf galaxy, forms Caldwell 42 within its own system. Step 2. This dwarf galaxy strays a little too close, and the Milky Way's immense tidal forces rip the smaller galaxy apart. Step 3. The host galaxy is completely assimilated, but its dense, ancient globular cluster, Caldwell 42, actually survives. It remains as this orphaned relic, just plunging through our halo. Our outer galaxy is essentially a chaotic, cosmic graveyard of these devoured worlds.
Which really leaves us with this final, profound thought. If Caldwell 42 is just one surviving core from a long-dead dwarf galaxy, how many other ghost galaxies make up the Milky Way? The next time you look up at the night sky, realize that you aren't just looking at stars born in our own galactic home. You're actually looking at the scattered remnants of devoured worlds. Thank you so much for joining me on this explainer, and as always, keep your curiosity alive.